So yesterday we learned how to graph polar curves by hand by tediously plotting a lot of points. Today we're going to just look at different shapes of polar curves. We're going to use our calculator to show us what they look like. We're just going to investigate a little bit. We're also going to talk a little bit about a transformation, an easy transformation, I guess we could say, to polar curves. So when we want to graph in polars, the first thing we have to tell the calculator is that we're graphing in polar. So we need to go change our mode. If you're on an 84, you're going to hit your mode button, and you're just going to go down to where it says POL. That's like maybe like the 5th or 6th row down, and it's like the 3rd thing over. But on the Inspire, we are going to add a graph page. And right now it says f of x. We don't want f of x. Just like on the 84, it'll say y1. We don't want y equals. So I'm going to hit menu. I'm going to go down to number 3, which is graph entry. And when you look at this list right now, we're in functions. And we're going to go down. We see number 5 says polar. And that changes. I mean, now it looks, I think, a lot different. So now it says r of theta equals. And then underneath it, it says theta right now is going from 0 to 6.28, and my theta step is 0.13. That's what I want to talk about first. Okay, if you are going to be graphing in radians, that's going to look a little bit different than if you're graphing in degrees. And by the way, the same thing is going to happen on an 84. I just don't have an 84 with me. So, but we'll talk about where to get this. If you are on the Inspire, well, doesn't matter, but if you're in radians, then you want your theta going from 0 to 2 pi, which 2 pi is about 6.28. And you want your theta step to be something small, like what it is right now is approximately 0.1. And I'll explain this as we go. Okay. If you are in degrees, we want, just like we were in yesterday, right? Yesterday we were plotting these by hand and we were in degrees. I thought it was a little bit easier to type them in the calculator. We want to go all the way around the circle, so we're going to go from 0 to 360, which in that case we're going to make our theta step about 1.0. 1-ish, 10, probably not great, 1 to 5. Okay, and I'll explain this as we graph. On the Inspire, again, I will write this down, where to get these things from. On the Inspire, it's in the entry bar, right, where we go to enter the equation. On an 84, it's in the window. Right, when you go hit your window button and you change your window, usually it says like X min, X max. Well, now it's going to start with theta min, theta max. So your theta min will be 0. Your theta max will, depending on what mode you're in, will either be 6.28 or 360. Okay. Okay, so that's the first thing. So let's come over here and we'll talk about some of these things from slide 1 as we go to graph. So we're going to talk about some Rose curves first. It says use your calculator to find a complete graph of r equals 3 sine of 2 theta. Now, my calculator is in degrees, but right now I'm only going from 0 to 6.28, like 0 to 6 degrees. That's small. So I either need to change this to radians, or I need to change this to, say, 0 to 360, which is not a big deal. You can get down there and you can change that. Now I'm going to hit tab again. Oh, it didn't change it. Oh. Well, then let's make it easier. Let's just go change this into radians. That's the easiest fix. Okay. I may not have hit enter the right way. Okay. So let's go graph. R equals 3 sine of 2 theta. Theta is going to be where our pi button is. We can't just type in an X. So go hit your pi button, and it's going to pull up this menu that we've seen before. And we're going to go all the way over and grab that theta. And look at that little rose curve. In fact, very similar to one we graphed yesterday by hand. There are 4 petals. It is a 4-petaled rose curve. I've got pen on my screen, sorry. So let's talk a little bit about the theta step while we're here. So I'm going to hit tab again and go up. And I just want to show you what that theta step will do. So right now I asked you to keep it kind of small at like 0.1. but let's say it was just 1. See what happened to our graph? It got very linear, right? It got kind of jagged. In fact, it's more like a connect the dots you did when you were a kid, right? When you connect one point to the next point, you would draw a straight line when you were a kid, right? And then so whatever you were graphing was very kind of choppy. That's what we did. We said, look, we want to go graph points, and I want to graph points from 0 to 6, and I want you to plot a point every 1 unit. Well, it's just not cutting it for us, right? To plot every 1 unit. So we're really only graphing 6-ish points in a sense. So that's why we want to keep that theta step small, like 0.1, because it'll plot more points, which will smooth out the graph. Okay. While we're here, let's go ahead and change the window a little bit. Just again, if we're going to try to find a complete graph, look at that word up there. Find a complete graph. That means I want to see it all, and I want to fill the screen. I could manually change the window, and I don't need to go all the way to -10 and 10, so I could go from like -6 to 6. But we could also go to menu, go to zoom, which is number 4, and then there's one called zoom fit, and you have the same thing on your 84. There's a zoom fit, so you could just type in the letter A, and it will change the window. The problem with zoom fit is it's going to skew the graph. And you know what I mean? If it's supposed to look like a circle, now it's going to look like an oval. So that's one thing to keep in mind with zoom fit. I'm going to hit Control Escape because that's, you see your little undo button there. So I went back to where I was. We could also go to, say, zoom. Standard is what we're on. There's my square. Sorry. Zoom square. Oh, because I didn't change my x-axis. We'll square up the window, so I had to go to zoom fit first. My fault. So again, we don't have to do any of this. I'm just trying to, show you what we can do to make it look a little bit better. So maybe I go zoom fit first, but then I go to letter B, which I could just type in the B, and then if I go to square, it will square that up. Basically, make sure it's not skewed. But now I just lost part of my graph. So again, I didn't have to do any of this. Maybe at this point I'll go from like -2 to 2. Oh, still not seeing it all. Wow. -5 to 5. Oh, it's horrible. We'll leave it at that. Okay, so that's my zoom fit. Again, all I'm going to do in here is just get a sketch. That's all they asked for. So there's my axes, and then I'll come in and just draw in that I saw 4 petals kind of going through the middle of each quadrant. That's not a great graph, but I'm not expecting greatness here. Okay. Now I want to see what happens when we change this slightly. So instead of 3 sine of 2 theta, it's 3 sine of 5 theta. So I'm going to hit tab. I'm going to arrow up, and I'm going to just change that 2 into a 5. I shouldn't have deleted my theta. I knew I needed that. Now I'm going to go back and change and go back and hit zoom fit again, so it fits everything in the screen. Okay. Well, it's still a rose curve. It's still a flower, but now it has 1, 2, 3, 4, 5 petals to it. So I'm just going to, just very quickly, I'm just going to go put this on my paper. We have one that's kind of symmetric around the y-axis. We have one that's a little bit above the x-axis on both sides, and then kind of down here, one down here, one down here. So the one thing that changed was the inside, right? We changed from a 2 to a 5, and we noticed the number of petals changed. Okay, I'm just kind of throwing some things out there. Let's take a look at these. So we just talked about rose curves or flowers. I'm going to talk about 3 different curves in here. We're going to start with limacons. There should be this little, I don't even know what it's called, that little French symbol that goes under the C. Sorry, my computer froze. That little French symbol that goes under the C, limacon, it makes it sound like an S. So I'm just going to go up and I'm going to clear this out. It's almost like our different families of functions, like our different parent graphs. Like we know we have exponential functions, we have parabolas, we have lines, we have cubics, we have sines. Well, that's what these are. These are all these new different just graphs. Okay, so I'm going to go back and hit zoom fit. And this is what we call a limmason. Now my calculator's off the page, that's why it looks like it didn't show us everything. I'm going to try to square it up. It may not do that, but okay, not great. It's supposed to be more circular, but we graphed one of these yesterday. This limmason is like a loop within a loop. So notice my x-axis is off to the left a little bit. And I've got this little loop here, and then we've got this big loop kind of out there. That's what we call a limmason. Okay? Just investigating different shapes. Let's start a lemniscate. So I'm going to hit tab and I'm going to arrow up and I'm just going to delete these things here. A lemniscate comes in the form of r squared equals something. Well, if we want to graph, it says r equals. So we're going to have to take the square root of 6 sine of 2 theta. Now, we'll talk about that plus or minus because we should technically graph both, shouldn't we? Menu, number 4, letter A for my zoom fit. Okay, so something kind of a muck is going on in the middle here. I want to address that. I'm actually going to go back and change that to a 0.13 and see if that fixes it. It does. Okay. He's just having a little bit of an issue plotting some points. Almost looks like this crooked figure 8. Almost kind of like a 2-petaled rose curve. But there's some different qualities to it. Now, remember, all I've graphed is the positive square root. So I should also go in and graph the negative square root of 6 sine of 2 theta. Right? Because maybe we only have half the graph. Oh, well, it didn't change much, did it? In fact, it just graphed a red graph right over our blue graph. So that plus or minus did not really change anything for us in this case. So a lemniscate is really just a figure 8. That is, again, not a great graph, but just kind of showing you what's going on here. Another type of polar graph is what we call a cardioid. Kind of imagine cardioid, the root word. I'm thinking maybe like heart-like, heart-shaped. So let's go up. Let's delete that and delete that. So let's go graph 2 plus 2 sine of theta. Okay, let's menu, zoom, fit, letter A. Okay, so look at my y-axis is way down here. And then when I go to drawing this curve, it's, use your imagination, it's a little heart-like, right? Heart-shaped. Okay, and that's what we would call a cardioid. That's an example of one. Now, all of these graphs, by the way, you know, depending on if we use sines versus cosines or different numbers, or if there's a plus versus a minus, things are going to change. And even if this graph was kind of on its side, you know, it would still be a cardioid. But again, just kind of playing around with some of these different curves and just really showing you about the calculator. Okay. The last curve I want to look at is what we call a spiral. So it just says graph r equals theta. For us, that's like y equals x, right? R equals theta. So I'm going to hit tab. I'm going to go up. I'm going to delete this. Excuse me. And I'm just going to, I shouldn't have deleted my theta again, but. And let's menu number 4, letter A. So zoom fit. Okay. So here's my x and y axis are for the most part in the middle. And it looks like it starts here to kind of, looks like a seashell, right? Or a spiral, hence the name, the spiral. So we hit zoom fit, and so we were able to see the entire graph. Interesting enough, though, and look at my little note, it says you may have to change your theta interval to see a more complete graph. We may have to change our theta interval to see a more complete graph. So I'm going to hit tab. Remember, right now, I'm graphing between 0 and 2 pi. Let's go down and just change that to go from like 0 to 16. That was just an easy fix for me. Now, it doesn't look like anything changed, but it did. You were quick to see it. Now we have a little bit more. Let's hit zoom fit again. Ooh, All right, so, and I'm going to kind of jot this down. Now, again, my axes are still in the center. And this one, I went from 0 to about 16.28. I just thought that was an easy fix. Let's try to graph this. It goes around once, twice, a little bit more. Right, and so if we think about the equation r equals theta, the radius equals the angle. So the bigger the angle, the bigger the radius is going to get. So if our angle is only going to 6.2, then our radius is going to only get as big as 6.2. Same thing happened here. Now, I could hit tab and I could make this go from, I don't know, to 116. And then you start to see this, all of this kind of get, well, you can't see my whole calculator, but it kind of looks like it filled in the spiral. So menu number 4, letter A. Woo! So again, I exaggerated some things there, but the idea is changing the theta window changes not only what we see, but how much of the graph it's going to actually create. Now, I'm not going to draw this perfectly, but so notice this one went from 0 to 116-ish. I just picked numbers, just trying to change it a little bit. Okay, so I didn't play around too much with changing that here because I felt like we had a complete graph. We saw it start and finish at the same place. It kind of finished its loop. But with the spiral, it kind of had left us kind of left off there. So by changing that theta window, we're able to see a little bit more. Okay. Let's flip it over here. Let's talk about lines, because lines were the easiest graphs we had in Cartesian or rectangular coordinates. So let's start with this one. So I'm going to, actually, I'm just going to start a new graph page. But when I do that, it's going to go back to function mode. That's why I have not been adding new pages. Okay, so I'm still in radians, but now I'm back in functions. I'm going to go to menu, number 3 for graph entry, and I'm going to go down to number 5. I'm going to graph the fraction 5 over cosine of theta, close that or get out of your parentheses, plus the sine of theta. And look at that. Now we can change the window if we want, but I see a line. Now, when our calculator graphs in polars, notice it's not drawing all the rings, right? We kind of said a polar grid can be laid on top of our Cartesian grid. So let's go to sketch this out. 1, 2, 3, 4. It looks like the y-intercept is 5, 2, 3. It also looks like the x-intercept is 5, which, I mean, I don't know. Look at that. So I don't feel horrible about estimating that those happen at 5 and 5. So there's my axes. Here's y equals 5. Here's x equals 5. And we've got that line. Okay. So the second part here says, could you write a rectangular equation? Well, absolutely we can, right? A line is y equals mx plus b. Well, if my y-intercept is 5, then my b is 5. And by the way, my next point is over here. That means I'm going down 5 over 5. So my slope is -1. Okay. We could certainly check that by adding another graph, but changing back to function mode on our calculator and seeing if it lays right on top of that one. Okay. Now part B says predict the shape of this graph. When we look at the two equations, the only thing that changes is what's in the numerator. The 5 turns into a -2. Well, maybe that means we have intercepts at -2 and -2. So maybe still a line, but now the y-intercept maybe is y is -2. So maybe it's y equals -x minus 2. That's our prediction. How do we check that? Well, we go to our calculator. I'm going to hit tab and I'm going to add, well, you know, we can just go up here and just change that 5 to a -2. And it's exactly what we predicted. Okay? Good. So we talked about a lot of different shapes. Notice we ended with lines because it's not like we could have predicted that this was a line until we saw it on the calculator. Okay? All right, so let's talk a little bit about some transformations. Okay, we're going to start with r equals 4 cosine of 3 theta. Okay, so let's do that. So let's add, just kidding, let's not do that. You can, right? But let's go back here. Let's just change this one. So I have r equals 4 cosine of 3 theta. I just didn't want to have to change my mode again. Okay, so it's a 3-petaled rose curve, and I want you to notice that the first petal it's kind of splitting the x-axis there. The other petal is in the second quadrant, and the third petal is in the third. Okay, now it says on the same set of axes, we want to graph this. So I want you to notice what changed. It's exactly the same. 4 cosine of 3 theta, but now it says 4 cosine of 3. And then notice what happened with the theta. It's a theta minus 45 degrees. So notice I'm in degrees. You have two options. You can change your calculator to degrees, or if you're in radians, just type in pi over 4. Okay. So I'm going to hit tab. Same set, so I don't want to delete that. So I have 4 cosine of 3 parentheses theta minus, again, I'm in radians, so I'm going to type in pi over 4. And it's going to pop up in a different color. Still 3 petals. Okay. What I am hoping that we see is the relationship. How are the two graphs related to each other? What transformation has been done? Right? Well, the center of that flower is still on the pole. It's still at the origin, but the whole flower has just rotated. Now we could look at it as a rotation this way or this way. We'll talk about that in a moment. This petal became this petal. I'll talk about how I knew. This one in the second quadrant became this petal, moving closer to the x-axis. This petal moved over into the fourth quadrant. Okay, so it is a rotation. We'll talk about that in a little more detail in just a minute. I'm going to relate it. I'm going to grab a post-it note here to this. What if we had asked, what if I had said graph y equals 4 cosine of 3x. I just changed the r's and thetas to x's and y's. And then I said 4 cosine of 3 times x minus 45 degrees. We know, because we've been doing it all year, when you have a change to the x, it's a horizontal change, and that would have moved our graph to the right 45 degrees if we were in Cartesian. We're not, though. We're in polar. So it did not move the graph left or right, right? The pole, the center of that flower, stayed in the same place. But remember how we use that opposite sign, right? If that said minus 45, we went to the right 45 degrees. Well, let's go back up here. If this says theta minus 45 degrees, that means we'd be going a positive 45 degrees, which for us, positive means counterclockwise, right? So we rotated clockwise, counterclockwise, pi over 4, or 45 degrees. One of the things we said when we first started this chapter 11 is that translating, moving a graph up, down, left, or right is actually very difficult in polars, but rotating them is super easy. And that's because we're just going to add or subtract from the angle, and that's what's going to rotate our graph. Okay? Oops, sorry. All right, so let's take a look at the last one. Here's a new polar equation. So we have r equals 1 minus 2 sine squared theta. It says write the equation that would rotate the curve 30 degrees counterclockwise. So we know counterclockwise goes that way. It's a positive angle. Well, we know when you change the x's, you do the opposite. So we have r equals 1 minus 2 sine squared of, not theta, but theta minus 30 degrees. Or if you want to be in radians, you could certainly write pi over 6, and I would take that either way. Okay. All right. Last question says, write the equation that would rotate the curve clockwise, so that's the opposite direction, 5 pi over 7 radians. So again, now we're going to be going this way, which would be a negative angle, but we're going to use the opposite sign. So r equals 1 minus 2 sine squared of, and we'll do theta plus 5 pi over 7. Okay. So, in summary, let's just kind of jot that down. To rotate counterclockwise, it's r equals f of theta minus your angle. If you want to rotate clockwise, it's r equals f of theta plus your angle. Okay.